Hey everyone, Grayson here with another informal debate slash discussion here. With this will be my second discussion with a flat earther. First time doing a non-formal debate. If you didn't see my last debate on modern day debate, go ahead and check it out. But today I'm with Iron Horse from Down Under. Um, Iron Horse, is there anything that you want people to know about you other than that? I mean, you identify as a flat earther, correct?
I identify as a human being who understands we live on a flat Earth. Yeah, I don't like to categorize myself as anything too much. Like
All
I'm
right,
just
fair enough.
a free individual who thinks for himself.
Okay, fair enough. So I guess the first question that I've been wondering is what started you down this path, or what was it that finally convinced you that the Earth is flat?
Oh, look, you could go way back to my late teens, really, when I read a book called Secret of the Ages by an author called Brinsley Le Pure Trench, and it was a book about hollow Earth. One of the chapters devoted itself to measuring the circumference of the Earth, and what they found is by suspending plumb bobs down towards the center of gravity, they thought that by doing that, you could measure how much closer together they are at the bottom and how far away they are at the top. And eventually you could just come up with a pretty simple formula to work out the circumference of the Earth. And they tried and tried and tried, and no matter what they did, they found that they always got further apart at the bottom. So that started me thinking more like the concave Earth, the type of thing, like we live on the inside of a sphere. And that gave me the sense, well, yeah, that makes sense. This centripetal force is pushing everything outwards, like when you spin a bucket of water around, the water is pushed outwards by this centripetal force. Well, that could actually explain gravity, because nobody knew what gravity was at that stage still, and today we still don't. So to me, that sort of made sense. That started me down the path. However, there's other complications, like we do see the sun set. And so for me to be able to reconcile that with a concave Earth, the sun would have to go back up again. And I finally, I've always been a really the person outside in nature, looking at the sunsets and looking at the landscape and seascape and that sort of stuff. And eventually I came to the conclusion that it's perspective that creates the illusion of the sun setting, and that can only work on a flat Earth. And that's when I became a flat earther, which was pretty well only quite recent. So,
Interesting. So you were kind of on this before it became a really big thing, because to my knowledge, the whole flat Earth kind of idea and movement really began to take off in like 2014-ish, 2015. And you gained a lot of traction then. So you were on this for a long time before that. Interesting.
Oh, my word. Yeah.
So, okay, there's a lot of directions that we could go with this, because I have. Are you aware of? I mean, you've been in this space for a while, so you've probably seen that in like land surveying, that they do take into account that plumb bobs, are not parallel. Then they diverge this way, not from the out in. I mean, that seems to be what you were talking about at first. So
yeah.
Have you looked into any modern land surveying where they do those calculations, or have you fact checked what you were reading as a teenager at all?
Well, it was known as the Tamarack Mine Mysteries, and allegedly back then, this was done by serious geodetic scientists too. This isn't just something done by your average miners or whatever. They were suspending them a mile deep, huge mine shafts, a mile apart from one another. Mm-hmm. And they sent their results to the French geodesic scientists and all the rest. And there's not much more mention of that in the book. And if you look it up on the internet, you'll find very little information. If you Google Tamarack with ACK at the end, mine mysteries, you'll find a little bit of stuff, but the internet really isn't that great a search engine for a lot of historical stuff we've done in the past. So as far as the modern versions of things are concerned, I think it's just a belief, because they haven't gone to the same lengths that these people were able to do 100 years ago, 120 years ago, where the funding wasn't such a big issue, whereas today to do anything, anything just costs an absolute small fortune. And
have you? I guess my question would be, and I will look at the Tamarack case, because this is the first time I've heard about that. So I'll try to see what I can find on the internet about it. But
you won't find much.
I've heard from land surveyors that they do this, and they in their calculations they have to account for the fact that distant plumb bobs are not parallel. So have you spoken to any land surveyors, like people that actually do this with like a theodolite, or like the people that have the equipment, like land surveyors? Have you ever spoken to one of them?
I haven't directly spoken with some, but I have come across quite a few. Like I generally spend a lot of my discussion time on Facebook discussion groups, and there's a lot of trolls, quite a few from both sides really. But there have been some who are genuine land surveyors who have come forward and saying, yeah, no, we never account for the curvature. They never do. You know, there's various things which might say, you know, you can predict it, or, you know, you can calculate for it. But really, when you bring perspective into it and everything, well, of course, distant things will look smaller. And so if you assume curvature, then the calculations that you're assuming you're seeing, even through a theodolite, you're still going to have distance diminution is going to be a thing.
Okay, so I want to get to this whole perspective thing. So just to wrap this up, I understand what you're saying, where on small scales with plane survey, you don't really have to account for the curvature of the Earth because it's such a small scale that local geography is going to be a bigger deal than any Earth curvature. But for geodetic surveying, for surveying over large areas, it is my understanding that you absolutely do have to account for the curvature in those calculations. So I just wanted to, I guess, make sure we're differentiating between planar surveying and geodetic surveying. But the sunset was a point that I brought up in my last debate. It's something I'm very interested in. So I would like to understand how you think that perspective accounts for the sunset. And in that debate, what I brought up, because I did bring up the idea that some people say that perspective can explain the sunset. And my biggest question about that was, why is it that we don't observe the angular size of the sun getting smaller, which would be, if this was an effect of perspective, then we should be able to see at sunset the angular size of the sun getting smaller and smaller, right? Did you agree with that?
No.
Okay.
So
I guess not.
You're jumping the gun a little bit too fast, I think, because we were talking about, you know, angular perspective with surveying. So before we go too much further, you know, what we really should consider is how much curvature drop should exist over how much distance. So land surveyors generally don't do more than 100-kilometre blocks at a time. 100-mile blocks at a time. I'm used to kilometres, but I'm also used to doing a lot in miles. So 100 miles in the globe curvature calculator, there has to be more than a mile of curvature drop. Now, that's a huge amount of drop. The world's tallest building, the Burj Khalifa, is about 1/2 of a mile tall. So we're talking over 100-mile distance, about 2.5 Burj Khalifas of drop. And that's never accounted for in any amount of surveying. They just assume it, that when you put your 100-mile pieces together, that curvature exists. But no, none of our experiences. We can travel, like 90 miles is the distance where 1 mile of drop first occurs. So we could travel 90 miles, and we have to assume from going from one end back to the other, we have gone up and down a mile of drop, which is a huge amount. And it doesn't exist. It's never been detected. It has to be compensating for that somewhere out of sight, out of mind, somewhere beyond the horizon, where we just imagine that this curvature must exist, because we never see it. It appears flat. It ramps up to eye level. That is how perspective works in every single case. So if you can see 100 miles, it will be at eye level.
Okay, so two things with this. So have you seen there are multiple people online, land surveyors and amateurs, that have done these measurements showing the curvature drop that you're talking about with a theodolite. So they'll go out with a theodolite, which can measure the angles, right? And they have it posted at horizontal, and then they have another sensor on the other side of a lake or something, like a mile away, say. And then when you look at it through the theodolite, the other one, that they're both the same distance above the water level. Okay. But the one, when you see it across the lake, it's much lower than the horizontal plane of the first theodolite. Have you ever seen the experiments like that?
I have never seen that. Everything I have seen shows, if they use lasers or whatever, that they are at the exact same level.
Let me see if I can maybe pull that up here. But again, I don't need to lay this on you last minute if you haven't seen it before. But
yeah, all I'm saying is that if you account in the perspective and distance diminution, which is the thing you're bringing up, is why you think the sun should shrink, is that the diminution effect is going to make the space this way and that way all shrink, and so it will appear smaller and so forth in the distance. And the theodolite is a very clever instrument which takes a lot of that factor out of the equation, so that what you're really showing is only your elevation. So the amount of drop you'll see in a theodolite is your altitude. You know, so if you see the horizon slightly below the center of the theodolite, that's your altitude. And if something was as high as where you are, say you're viewing from 50 feet high and there's something 50 feet high in the distance, then they will be at the same height. So yeah, it'll be interesting to see if you've got something over a long enough distance, which is pretty hard to do because most things can't see more than maybe 25 miles or something. You know, that's a pretty good line of sight to be able to see is 25 miles. But to be able to see over 50 miles and see things at the same height, you should show two theodolites will appear at the same height.
Yeah, so I'm trying to look this up. I know that this was done by land surveyor Jesse Kozlowski. I'm trying to find his page on the online right now, but I know that when he did it, he had two theodolites, and they were both on a big lake. I think it was maybe 1.5 miles or something, and he basically controlled for like he made them the same height relative to the water surface of the lake. So they were like right there on the shoreline, and he measured from the surface of the lake to the height of the theodolite and made it the same for both of them.
I think I might have seen that. Yeah.
Then he pointed them at each other, and the one was lower when you look through it. It's lower than a horizontal plane. So, but again, I do believe that land surveyors and amateurs alike have done similar kind of experiments.
It does beg the question, though. Like I said, so your position, your solipsistic position on the Earth, is obviously always on top of the ball. And so the other theodolite then is obviously going to be slightly lower because of the curvature drop. But then from that one's perspective, it's on top of the ball, so you're lower. So, you know, how does it work? Which one's lower and which one is higher in reality? Because 1.5 miles isn't very much at all. It's,
well, it's a little bit of a malformed question, right? Because like they're both, like if you look at one, it's going to be lower than the horizontal plane of the other, and if you just switch which one you're looking at, the other one's going to be lower than the horizontal plane of the other. Because on let me see if what
about the Bedford level experiment that they did way back, where they measured over 6 miles, and they found if you kept the telescope at eye level, that the flag receding into the distance stayed at eye level for 6 miles. It's only when they did that, the thing of using a bridge over double the height at half the distance, that was able to confuse the viewer, saying, oh, well, if we account for refraction, whereas really when you're using, because perspective has two aspects, the distance diminution and convergence, if you have something more than twice your height, then the halfway point is going to appear higher than it should do than if you kept it at eye level. It's not going to get as low at the halfway point as what it will appear low at the full distance. Yeah, so over 6 miles, the halfway point at 3 miles will be eye level at eye level. You go 6 feet above you, and it will be exactly equal. But then when they go 12 or 13 feet high, then that's going to give an artificially raised height, which will make it look as though there's a hump in the middle, which is how that fellow that swindled Rowbotham out of the bet was able to get away with it, because he was a professional surveyor and he obviously understood that little trick of the book. And that's the same thing what Jaron got done by on that beyond the curve.
Yeah, I'm not exactly familiar with what you're trying to describe here, but you do bring up an excellent point with refraction and its ability to make things visible for longer amounts of distances. So what I wanted to show you with that, I'm still looking for the page on what Jesse Kozlowski's experiment did. I didn't have, since this is an informal discussion, I just wanted to see where the conversation goes. I didn't really prepare certain points to be talking.
Either did I. No, but I don't believe what those words you just put in my mouth about refraction allowing us to see further.
Well, I think is what I wanted to show you.
That's a huge hoax.
So this is the world record holder for the longest ever, the longest
73 miles. Yep.
the longest
It gets far.
distance line of sight photograph ever taken, right? So
Yeah.
this is the world record holder. So the distance is 443 kilometers to those mountaintops here. This is a mountain. This is somebody photographing the Alps from the Pyrenees,
Yeah.
and I'm curious to get your take on this, because the photographer who did this, they're not a flat earther. They understand that they were only able to take this because of refraction, and this is a hard photo to take. Right? It's not like anybody could just take this photo. The photographer had to continuously monitor the weather conditions and calculate when he should take this photo for the optimal refraction so that this photo was possible for him to take. So he's using like simulations of a heliocentric globe Earth in order to calculate when he should go up and hike up into the Pyrenees to take this photo. So what is your take on that? Like, the guy that has the world record for the longest distance photograph, and he completely understands how it works on a globe. The calculations all check out. He's done them. So why is it that I should accept long distance photography as proof of a flat Earth if the world record for the longest distance photography is completely explained by the globe?
Well, it's absolutely not explained by the globe whatsoever. As I said, that at just 90 miles of distance is the first mile of curvature drop which should exist, which would be impossible to see over that amount of distance. Like, the curve is exponential, and the 8 inches per mile squared is a pretty accurate formula. So if you did 273 times 273, then multiply that by 8, then divide it by 12, that will give you the number of feet. And it's the amount of curvature drop which should exist, and yet you can see quite clearly that the horizon is more or less eye level. And the only reason that he was able to capture such a good image at that particular time is because he is highly elevated, so the atmosphere is a lot less thick at the time and is backlit by the sun. So because it's that sunset, having that little bit of backlight, it creates a silhouette of those far distant mountains. You can still see it's quite hazy and whatnot, but it's only possible on a flat Earth. If the Earth was curved the amount that we're told it should be curving, that picture would be 100% impossible.
Right. But on the guy's website, the photographer that made this picture, right, or like that took this picture,
it doesn't make him an expert, though.
On his website, he has the simulations on a globe, like for the exact refraction conditions of this photograph, for the exact location, the latitude, the longitude, the altitude, the target distance. He has it all mapped out using the globe model, the accepted consensus formulas, and it all works out to show exactly why this photograph was possible. So it's like the guy who takes this understands how this works on a globe model. So you're just rejecting what he is calculating?
Well, yeah, because if you've already preconceived the notion of what it is, if you've already got that preconceived bias in your head, you will find a way to make it match. It's the Eratosthenes experiment, basically. If he was setting out to prove that the Earth is flat with a local sun, then the results he got would prove exactly that. And so if he was out to prove that the Earth is flat and he was able to see that far, he would do that. But because he's already preconceived the globe, he's going to find a way to make the experiment match. It's simply all you've done. There's no way refraction is capable of doing that. Like, refraction is a thing where, say you've got a glass of water or a fish tank or whatever, and you view things from a different angle of it, then parts of it are going to be disjointed or shaped completely different. The atmosphere is a gentle gradient. It is not like a sharp line of seeing between water and atmosphere. It's just, it's basically humidity. And refraction is trying to say that then it turns the atmosphere into some sort of magic periscope. So a periscope has two mirrors in it. The first one inverts something, gives the mirror image, and then the second one puts it back up again. How would the atmosphere act as some sort of magic landscape periscope?
Okay, I'll show you exactly.
Something that refraction can do. If you can show me how you can do that, by all means.
I'll show you exactly here. Here's an example, right? This is just a tank with, I think it's maybe sugar water. And the key here, right? You can see that refraction is causing this laser light to bend. It's going in an arc, exactly like
that refraction. How is that refraction there?
Yeah, I'm explaining, because you see here that it's a variable concentration solution, decreasing upwards. So there's a higher concentration at the bottom of the tank and a lower concentration at the top of the tank. And
what, of sugar?
Yes, of sugar. And what refraction dictates is that light will always bend in the direction of higher concentration. So on Earth, in our atmosphere, there's typically a higher concentration closer to the ground and a lower concentration higher up. So all light will naturally bend towards the curve of the Earth as it travels. So you can see here in this picture that the light ray is bending in a curve because of the concentration gradient. So
but
this explains...
You're still missing the point, though, aren't you? That's fine for light to be able to do that. Like, I've got no problem if you assume a curve, the light can show over it. But if you've got physical Earth in the way of something, then the light might show above it, but you're not going to see through the physical stuff in front of you to see through the curvature to see an image of the things that are actually blocking the light. Those mountains in the distance are blocking the light. So all you would see is the glow of light with some shadows, maybe where the silhouette of those mountains in the distance would be.
Wait. Why do
coming up above your physical horizon? That's all caused by curvature.
Wait. Why do you think that the mountains are blocking the light? I mean, you admitted that it's being backlit by the sun. So the sun is hitting those mountains and then bouncing off and being refracted over the curve of the Earth to your eyes. So at no point are the mountains ever blocking any light.
They are. They're backlit. They're lit from behind. That's why they appear dark. That's why they're dark in the first place. The sun is setting behind them.
No, it's not. It's not.
It is. Remember, it is.
Just remember here for a second that this is a photo of the Alps from the Pyrenees. So the sun sets, it rises in the east, sets in the west. So the sun is behind the photographer because the Pyrenees are west of the Alps. So
I don't know about that. I'll take your word on that.
He's facing east. I can pull up. I think he's got a map of where this was taken. Yeah, here we go. Let me share my screen here so you can see where that world record photo was taken. So you can see right here. It's sort of northeast. So he's standing down here in the bottom. He's standing right over here in the Pyrenees Mountains, and he's taking a photo here. Over the French Riviera to the Alps. So he's facing northeast at sunset. So the sun would be over here to the west in this direction. So the mountains are not blocking any light.
Okay, well, that's not what I've heard about the picture. So
and I would like this picture. This is on the photographer's website, by the way. But I just want to be clear that
well, where
you could do this experiment yourself, right? Wait, you could do this experiment yourself, right? If you have a hill anywhere near you, you could try to send some electromagnetic waves, like radio waves or something, over the hill, and you see if you can detect them on the other side of the hill. If they hug the surface of the hill and go over it and down into the valley on the other side of the hill, then you could tell that the radio waves traveled and hugged the surface of the hill up and over.
And
so
that
you can
just
do this
says
yourself.
nothing about curvature, though, does it?
What's
and
that?
as I've said, the amount of I said, well, that proves nothing about curvature, then, does it?
No, you're right.
Because we know mountains are topographically curved. You know, that's the only example we've ever seen of actual land curvature is mountains and topography. So, but at that sort of distance we're talking about here, you know, the best part of 300 miles, the amount of curvature drop that would exist would have those mountains hidden completely beneath it. There's no way that light coming from behind you could then also act as a magic periscope. It might go over that curve and light those mountains, but you still wouldn't see it because of all that physical curvature between you and those mountains. So either way, it doesn't work.
So the reason, so on a normal day, you cannot see those mountains. On a normal day, those mountains are not visible. They are behind the curve of the Earth. The reason why this guy won the world record is because he was continuously monitoring the weather conditions and calculating the refraction so that he knew when the peak levels of refraction were, so that he knew I need to go take this photo now because refraction is at maximal value. And so he went, he photographed it, and he could see it because of the refraction. That's the explanation for why
well,
he was.
That's a cool story. It's a cool story, man. But there's people today using infrared cameras that are able to get 600 miles, more than twice as far. And they don't have to account for refraction then because they're using infrared. It can see through all that stuff. All they're really seeing is pure light and heat.
Well, I just want to say that you do still have to account for refraction with infrared. The refraction will still bend infrared light.
All right. So we've established then, obviously you disagree, but you've basically then said that we can see way too far than we should do if the Earth was a globe. And now you sort of...
Wait, pause.
Well, you said there are exceptional circumstances that will allow you to, but that should be impossible to see.
I know. I do not agree that they should be impossible. And I just explained why not. Because of refraction.
In very rare circumstances that you might be able to overcome those ordinarily impossible reality of the globe curvature. Like the amount of drop is phenomenal. Like I'm just going to do a quick calculation here.
And there's really good calculators. Let me see if I can pull this up here.
We're talking nearly 50,000 feet of drop that should have existed between those mountains. That's 49,686 over 273 miles. That's the amount of curvature drop that should exist. And I don't believe those mountains are even that high. I think off the top of my head, Mount Everest is barely even that high. So
yeah, but you're not accounting for refraction in those calculations. That's the whole issue.
Well, okay, the magical refraction, and I simply don't believe it. It is because it's physics. But even the example you showed says light bends down. It's not lifting something up in the distance. It's bending down. It's going over the curve and bending down, and that's the light itself is doing that. It can't see through physical blockage of the Earth. You're looking down through the Earth to see those mountains, which, according to the curve, one's pointing up that way, one's pointing up that way. Then, they're getting up higher isn't actually helping you to see further over the curve. You're still going the wrong way.
Okay, I'd like to do something with you here, because you quote this 8 inches per mile for for curvature, but you don't account for refraction. So I want to show you here. Here's an online calculator that does account for refraction. So we could plug in here our observer height, our target distance, target size, and we can mess around with the refraction. Look here. When we move the refraction around, you can see on the thing, you have eye level, you have this object, and you have the horizon here. Just by me messing around with the refraction coefficient here, you can see I'm going through weak refraction right now, and that stronger and stronger refraction. You see that more and more of that object becomes visible. So this is not magic. This is physics. It's completely calculable.
Mm-hmm. So I guess you can program anything into anything though, and get the results you're looking for.
Well, so just so I can be clear, this is open. You can see the source code for this. You can see what formulas they're using, and they are using real physics formulas. They're not backing into this to try to make it work or anything. This is what we understand from how physics works. This is a great calculator. I encourage you.
But this isn't physics. This is completely optics. Physics is completely different. Physics is pure without any optical.
I just want to be very clear that optics.
Don't call it physics. It's optics.
I want to be very clear that optics is a subfield of physics.
No, well, physics is about the physical matter, whereas optics is more about the light and how we see things.
Again,
they're two completely different subjects. Really,
light is understood in physics. We have physics formulas to describe light, and just to be very clear here, there have been Nobel Prizes of Physics awarded in optics, in quantum electrodynamics, which is understanding how light works. So yes, light is part of physics. Physics is not just physical matter; it's also radiation. Radiation is still studied within the field of physics.
Yeah, it's a blurry line then, isn't it? Because then you've also got chemistry, and there's also biology, and technically they're all one and the same thing. So when you say physics, then I assume just pure physics, the physics of motion, the physics of mass, the physics of weight, and all that sort of thing.
E
optical
equals
stuff
squared
to me
physics,
isn't really physics.
E equals MC squared
it's That's sort of crossing the boundaries, isn't it? That's sort of saying that energy
I don't think it is
matter, and I don't think that it's the same thing.
Oh, physics is the study of matter and radiation. Light is radiation. So,
possibly.
So I just wanted to be clear on that front. If you like, you also, I did still have a little bit more questions on the sunset, but I'm also curious.
Yeah, I'd like to jump back to that now.
I also did want to get eventually to discussing about gravity, because gravity, as we understand it, would necessitate that the Earth would be a spheroid, right? Just because the Earth has so much mass that gravity would compact it into a spherical shape.
That's an assumption, isn't it? Like, there's absolutely nothing testable, verifiable to say that mass itself becomes a force of attraction. It's an absolutely made up belief that had to be invented in order to make the world spherical in the first place. If you assumed it to be flat and stationary, then it doesn't have to be globular at all. You can just assume everything finds its place according to density and buoyancy, and it will do so without any need of attraction or the thought that something that directly opposite you on the other side of the globe is going to be falling the complete opposite direction. And there's millions of things that can debunk gravity. So
the Cavendish experiment measured the force of attraction between masses, but I also want to ask you about what do you think of our observations of solar systems? Like, when we look out into space, we can see solar systems where you have planets that are spherical, that we can watch them orbit the star. So what is causing them to orbit?
Can we though? I strongly suggest we don't see that whatsoever. We're seeing lights out there doing their own little thing that have nothing to do with what's the ground beneath our feet. I don't believe any of them are terra firma whatsoever. I've got no reason to believe they are. Nobody's ever been to one. No one's brought back samples. All of that is just completely up there. It's airy-fairy theoretical science, and it's got nothing to do with what we're talking about, the shape of the Earth. So to look at the lights in the sky to prove what's beneath your feet.
So the first exoplanet was, I think, founded around 1995, and since then we've categorized over 5,000 exoplanets that we have seen ourselves.
Who's we?
The human species.
So the authorities, the high priests of modern scientism, who's
no. So, for example, the James Webb Telescope is open. The James Webb Telescope is open. You can it's open observer time for anybody that applies. They give it to whichever person provides like a very worthwhile proposal. But again, anybody, this is open for lots of people in Australia, PhD students around the world. People apply for time to use the James Webb Telescope, and you get maybe.
So is there like a professional documentary being made by one of these people who can show this and prove that it's physical planets and not just lights? Say, for example, I said that all the lights in the sky are souls. They're ascended beings who are great people on Earth, and all they're really doing is adoring their own father figure, their parent, their first ancestor, and that's all they are. They're just lights in adoration around a greater soul. What if I told you that? You couldn't prove me wrong,
Well, it would be a little bit strange given spectroscopy. So with spectroscopy, we can see what kind of elements that these distant bodies, whether they're stars or planets, are composed. Again,
that's presupposing that, you've already presupposed the answer. What if I said, well, that's just a quality of the vibrational frequency that they give off, and when they react with the atmospheric gases that we see them through, that's what gives us the colors we see. I could say that it's a frequency thing, and light is frequency. They're all just light beings, and their particular frequency, their song, whatever they're giving out, that's what we see, and you can't prove that wrong either.
So then would you say then that it's a coincidence that, for example, here on Earth, we can replicate the various spectroscopic signatures of elements here on Earth? Like if you do spectroscopy with a bunch of neon gas, it will always produce the same spectrum. And then if we look up in the stars and we see that spectrum exactly, then why would you not think that that would be neon gas out there?
Because neon gas is what's in our atmosphere. And that particular frequency is what is stimulating the neon what's called ionization that creates it, makes it fluoresce, sometimes sparkle and all that sort of stuff. And it's the frequency of the vibration they're giving off through our atmosphere that gives them their color. So it works just as well.
In that instance, then, we would always expect all spectroscopy to reproduce the elements in our atmosphere. But in reality, depending on where we point it in the sky, again, it's all passing through the same atmosphere, but depending on which stellar objects we pointed at, we get back different spectrums. So
that's right.
It can't be explained by just interactions with our atmosphere.
It can, because they are the ones creating the frequency of what they electrostimulate. You know, it's like you can create a whole range of different light bulbs depending on the constituents of the number of different gases you put into them, how much nitrogen, helium, neon, you know, xenon. There's a whole range of different noble gases, but it's in this case of the atmosphere, it's what's stimulating it. It's what's creating, that's the power source. So that's creating the frequency, the vibrational frequency that we're seeing through those gases, and the ones that it particularly stimulates according to its own vibrational frequency is what we see. So it's not saying that's what that's made of. It's just saying what we're seeing through the atmosphere that particularly.
But shines. Again, I don't understand. If it's the atmosphere that is causing these spectrums to be observed, then why wouldn't it be the same in all directions? Because it's the same atmosphere in all directions that we point.
In daylight it is, because the sun is such a powerful entity that it creates such a powerful frequency and vibration that it stimulates the whole lot of them at once, which creates the sky to appear blue. But when it's out of range and the neons finally fade, that's the twilight sort of colors from the influence of the sun, then all we're left with then is the lesser frequencies of different things. Every single one has its own different frequency. And so it's stimulating its own particular part, which we're seeing through our own, you know, solipsistic view towards those stars. That is the frequency that we see. And if we go above the atmosphere, as we see in high altitude balloon footage, you generally don't see any stars at all. And if you do, they all.
You know why that is, right? It's just because the Earth is too bright.
That's possible, but if you do it at night, it's not that bright. Like we see stars at night.
Yeah, it's still pretty bright. Like when you're, you know, if you're shining a flashlight in front of your face, you're not going to see a bunch of dim lights.
No, that's right. And that's daytime. That's daytime. But at nighttime, when that flashlight is gone, you will see those dimmer lights in the distance. And that's why we see them at night.
Yeah, from Earth. But if you're going out into space, I think that you'll still find, like, I mean, you can't even see the stars that are surrounding the moon because the moon is too bright. Like, I don't know. I don't think that
it's an exposure thing.
Mystery,
yeah, absolutely. Like exposure is a tricky thing because our eyes automatically adjust as.
But it sounded like it sounded like you just admitted that we are receiving, like, the spectrums that we receive from these different objects are unique to these individual objects. It sounded like you were saying that at night. And so my question is then, why don't you think that those spectrums contain information about their elemental composition? Because you can pass those spectrums through a Fourier transform. It's just a mathematical procedure that breaks it down into different components. And those components exactly correspond with, here on Earth, the different elements, what kind of spectrums each individual element creates. So why don't those unique spectrums that you're talking about, why don't those show information about elemental composition?
Well, it's 6 of one, half a dozen of the other. Like, you could assume either. You know, like, from your perspective, yeah, it seems entirely possible that's what they're made from. But from my perspective, I could say, well, it's entirely what they're stimulating in our atmosphere, and that's what makes them look that way. So you can't really make a conclusive argument either way.
No, but you can, though, because I feel like we're going in a little bit of circles here, because I was explaining, if it is caused by our atmosphere, then it should be the same in all directions we point it. We should get the same spectrum everywhere we look because it's the same atmosphere.
Okay, like if you've got a bunch of different Christmas lights on a tree, right? They're all different colors. How come they're not all the same color? Because they're all putting out a different frequency, aren't they? They're all a different color. And that's what the stars are doing. They're all individual frequencies. They're unique to each and every single one of them.
And that is determined by the same thing that is determined in the Christmas tree lights. It's determined chemically by their elemental composition.
You can describe it chemically, but it's not necessarily like a chemical thing. And the atmosphere, again, is basically a chemical composition. So, again, you're back at square one. It's still the same thing. It's just a matter of interpretation.
All right. Well, to avoid going in circles on this, I'd like to move on to gravity, since you had mentioned that you consider gravity. You can explain the same phenomenon with buoyancy and density, right? That's what you were saying?
Well, I just call it relative density.
Okay.
And I say, rather than a force of attraction, I say the force is resistance.
So my biggest question, because I've heard people bring this up before. My biggest thing that I don't understand about that is why down? Why the downward direction? Why not up?
Okay, well, I'm glad you brought that up, actually, because that image you used before this video started, that you had as your thumbnail, it's called, what do you call it, based reality? Is that?
Based theory. That's the name of my channel. Based
theory, sorry. Yeah. The word based, you have to have a base. Everything is built on a base. That's basic, you know. So in music, you've got the scale, you've got your bass notes, they're the lowest, they're the deepest. And then as you go up in scale, they get higher and higher, lighter and lighter. Yeah. So the more dense something is, the more towards the base it goes. And the Earth is the base of the universe. So everything is built on the base. That's the basic understanding of flat Earth. So everything has a downward tendency if it's more dense. If it's more light, it's more upward tendency.
So my question, though, is why? Why wouldn't we have the base on the top instead of on the bottom? Why?
Well, if you stand on your head, we do. You know, the base is on the top, and everything light is floating down. You know,
when I drop an object, it always goes down and never goes.
But if you're standing on your head, it's falling up. You know, like all that is a human construct. What we do in anything scientific is we make the observation first. We make repeated observations. We do experiments. What do things do? This is what they do. Then why do they do it? Okay, well, it's more dense than the medium. The air is insufficient to resist it. So it falls to a place of most resistance because it's already more dense and it's already down there because it's already done it because of natural physics. So the why down is self-explanatory. It just does.
I don't think it is self-explanatory, though. That's what I'm questioning. So if we think about a vacuum, right, and an object in a vacuum, every single direction in that object is equal density. It's just the density of the vacuum. So up is the same density as down, is like relative density. It's the same in every direction. So why does that object move down? And if you're saying, well, if I sit on my head, it goes up, then I'll change it. Instead of saying down, I'll say towards the Earth. Why does it go towards the Earth if
hang on a sec,
the same density in all directions?
Go back again to this vacuum. Can you describe this vacuum situation for me?
So just, you know, it's like a big vacuum chamber.
A vacuum chamber.
All the air has been sucked out.
Okay, sucked out of the chamber.
Yeah.
So the chamber is the important thing. It's got solid walls, impermeable walls, and it's got a solid base.
Okay.
And that's why you can have a vacuum situation to extract the air from. And so then if you have a thing in it, you've actually created a zero resistance environment. So it's going to fall to the base every single time without any resistance whatsoever, which is why even a feather will fall at the same speed as a bowling ball because you removed all resistance.
Yes.
If you increase the resistance by putting air in there, the feather will waft. You fill it with water, well, the feather will float. You know,
I agree with that. My question, though, is what determines the direction? Why does it go down instead of going up or to the side?
Well, because that's the way it is. You know, that's the way things are made. There is a universal up and a universal down. I mean, left and right is arbitrary because my left is your right, but up and down is universal direction to the base.
So it sounds like,
and you got what's above the base.
Do you understand why I'm not satisfied with this? Because your answer is that's just the way it is. But in our understanding of gravity, we actually have an explanation about why down is down.
Yeah, but that's a theoretical though. That's a theoretical thing to say that, over there, 6,000 miles over there, things are falling that way. And 6,000 miles over there, things are falling that way. And then another 6,000 miles, things are falling that way. That's a belief. That's a theory. In reality, with every observable experiment we can do, things fall that way. That's the only way things fall, unless there's another force acting upon them, which will create a resistance which might blow them sideways or might cause them to bounce a different way. But without any resistance, the downward force is the way it is. It's just natural reality. You don't have to invent anything more unless you are trying to prove so hard that the Earth is a ball, and then you have to bring up all the other stuff. But without, invoking anything extra, the universal up and down is what we've got. And it's observable and testable and repeatable again and again and again. I
would say that invoking a universal up and down is invoking something extra, because that's not an assumption of like...
Okay, have you seen an observation of something falling sideways without another force acting upon it?
Well, it's always going to fall towards the center of the Earth, which is defined. That's the definition of down.
Yeah, but that's theoretical. You can say that, but you can't prove it.
So in the Cavendish experiment, right, that's a measure of like the effect of gravity, like from non-Earth objects, right?
It's just an extremely dubious experiment, that one, because they are all Earth objects. And that you're assuming then that one mass is going to be more attractive to that little mass than the massive mass underneath it.
No.
All that's happening is eventually that thing is going to come to rest, and it's going to come to rest against something, because on a balance.
Just to be clear, there's no assumption about it being more attracted to the smaller mass compared to the Earth. That does not come into it. What you do is...
It does.
No. So what you do is you draw like a diagram of every single force that's acting on that ball. And so you have a much bigger force attracting it to the Earth because like Newton's universal law of gravitation, there's going to be a much bigger force going towards the Earth. But on top of that big force, there's another force to the smaller object, the 350-pound object or whatever. And that is on addition, and it's an additional force on top of the attraction to Earth. So it's not like it's bigger. The attraction to Earth is still bigger in the experiment.
Yeah, it's just another assumption, though. It's, to me, eventually...
It's not assumed, it was measured.
But it's not measured. It was observed eventually that the little thing will come to rest. And there could be all sorts of other forces. Like you've got air is always in motion, Gases are a fluid always in motion. So they're going to create some sort of electrostatic charge. Eventually you're going to find some reason why things will come and stick together if they've got nowhere else to go. It's just inevitable. It's not a proof of anything. It's just what is most likely going to happen. And more often than not, the Cavendish experiment doesn't even work. It's when it does work, people clap and gee, woo, yeah, we got proof of gravity. But when it doesn't work, something went wrong. We'll try again until eventually you find a way of proving what you presupposed in the first place.
So what about a gravimeter? It's a measuring device that measures the strength of gravity right there locally. You can buy there are commercially available gravimeters like that you can buy.
I've heard of them.
But when you travel from one place to the other, and when you go up in altitude or down, the strength of gravity changes a little bit, and it can be detected by these machines. And the interesting thing is that the more matter is underneath your feet, the stronger that reading on the gravimeter will be. So if you're on the ocean, right, and you pass over an underwater mountain, now you have more matter underneath you, and the gravimeter will read a higher setting than when you're on the same ocean and you're passing over a trench. So you can look at this yourself, and it will measure a difference. So how is it that force or buoyancy, that density or buoyancy could possibly explain something like that? Because you're on the surface of the ocean for both of them, right? Same altitude, same elevation, same ocean. The only difference is that in one, you have a trench underneath of you, and the other, you have a mountain underneath of you under the ocean. But it reads, the actual physical measurement reads a different value. So how can that be explained without gravity?
Well, you could just change its name and call it a densometer, because it's just measuring the density of what's beneath it. So a densometer is just as good a name for it as a gravimeter or gravimeter. And the same, apparently I've heard the opposite happens is if you take it up on top of a mountain, it measures less. and yet you've actually got more mass because you've got the mountain all the way to the center of the Earth, and yet it's saying it's actually less gravity up at the top of a mountain.
But you understand why that is, right? Because look at Newton's formula for gravity. The radius squared is on the bottom. So the force of gravity changes with the distance squared. So that if you're farther away from that center, that's why I was saying it was important to do this on the sea level.
Okay. In the scientific model, as we've been told multiple times, if we shrunk the Earth down to the size of a billiard ball, it would be measurably more smooth and perfect than the average professional grade snooker ball. So we're talking negligible amount of difference at the top of a mountain to the bottom of a mountain. And you're saying that these instruments are able to measure to that standard?
Yes, they are. In fact, submarines... Maybe
they're just working off other things like pressure and the density of the ground beneath.
Submarines are actually able to navigate using gravimeters. Like just measuring the force, the strength of gravity. They can tell where they are on Earth because everywhere on Earth has a little bit different value for gravity acceleration. So just in measuring the difference in those accelerations, you can actually navigate and figure out where you are. So like submarines normally to navigate, they might have to surface to get like a GPS or satellite signal. But this is really advantageous for the military, right? Because you can stay submerged. You don't have to be contacting a satellite or anything. All you have to have is a gravimeter on board. And you can navigate. I mean, they do this in the military. You can navigate using only the strength of gravity. So, I mean, that's...
To me, that's just a cool story, dude. Like, it means nothing to me. Like, so what?
Does that not demonstrate the existence of gravity to you?
No, it measures density. It measures the depth of the water.
How would it be measuring density, right? Because in order to
because density determines the force of attraction, doesn't it? That's what gravity is all about. Is the more dense it is, then the more attraction it should have. So it's just a densometer. It's the same thing. Like the word gravity itself comes from the word gravitas, which means weight, and weight can be determined by the density of a thing times its volume. So if you've got a bigger, more denser volume, then you're going to have more gravity. It's just another word for it, but it doesn't prove that it's a force of attraction.
So I just want to be clear. Density alone doesn't determine its mass. So if you have a bunch of mass in a small area,
everything is mass. Dense, everything is mass. The density of the mass times the volume determines the weight.
Well, not everything is mass, but sure.
Well, it is. The density of the mass times the volume of the mass equals the weight of the mass. Saying it's mass is irrelevant. It's meaningless. It's just stuff. Mass just means stuff.
So light is stuff, but it's not mass, right? And we have measured...
Oh, well, is light stuff? Or is it just the...
it's photons.
The chemical sort of fluorescence of something by being electrostimulated that creates light, but it's not necessarily a mass. You can't measure.
We know that light is made of photons, and we can.
Do we?
Yes, and we can observe light actually bending around massive objects. I mean, this is a prediction of relativity.
But even so, even if light bent around it, it's still not going to make you see through that object, though. You're going back to that again. Is you cannot
see through it. There's no necessity to see through it.
But that's what you were saying with refraction is. You're saying that it is making you see through the curvature of the Earth. You're just going this way. No, of course you can't do it this way, but you think, oh, doing it that way, yeah, perfectly normal.
The light can bend over something because of refraction, because it's
what's the difference
going to be bending down.
What's the difference between over and around? What's the difference?
Well, you're not seeing through it if you're going over and around. That's not seeing through it. Seeing through it would be through it. If you're not, if you're going around it, you're going around it. You're not going through it.
So you're saying if you got a bright enough light behind the building, you can see around the building.
Why would I be saying that? Why?
Well, because you've said exactly the same thing with the mountains or the curvature of the Earth between you. If the light is strong enough on the other side of the curvature, you can see straight through the curvature. But if it's a building upright, you can't do that. Light will bend around it, but it won't make you see through the other side of the building. But how is curvature any different just because it's this way?
I don't understand why you think you'd be able to see through a building.
Because that was your argument the whole time with refraction.
I don't think that was my argument, since I don't think you can see through buildings.
But we can see through curvature. physical curvature of the Earth.
Again, I just want to be very clear. You're not seeing through curvature, right? So in your own model, right? There's a globe, a curved surface. Not in your model, sorry. In the globe model, there's a curved surface, right? And if you shoot light over here, it's going to be going this way.
Light over here.
But the refraction, because there's a higher concentration gradient closer to the surface, it's going to continuously bend down towards that surface and follow the curve of the Earth. So you're never seeing through any ground or material. The light is never passing through any material.
But all you would ever see then is that light. You won't see the physical object that was on the other side of that curvature you just showed it going over.
But you understand that that's how you see objects, is by seeing the light.
I don't understand that it could do such a thing as what you're saying.
I mean,
if
right now,
do it around the building, if I shine light and the light curves around the building, you know, I might see some fringe of that light. It's not going to show some person hidden behind the building by any means. It's, you know, it doesn't matter how bright the light is or how much refraction you add to it. It's not going to bring them into view because
you understand that every object that you see, you're just seeing the light that was bounced off of that object, right? For every
if they're in my line of sight, they have to be in the line of sight. They're not going to appear visible just because I see light reflecting off them, unless they're in my line of sight.
Well, again, yeah.
There's a bright light behind the horizon or behind the hill in the distance.
The point is,
I can see the light from it, but I won't see the light source itself. The source is basically what the light is.
The
what you're trying to say
is that refraction changes the line of sight. That's the whole point. Is that you can
sorry.
Because of refraction.
It doesn't. If you see a fish tank and you see, you know, through the corner of a fish tank, and you see a fish on one side and a fish on the other, that's refraction.
Look,
you're seeing two different images
right here.
Light being bent, but you are not going to see either of those fish if they're not in your line of sight, even though it's only one fish.
I'm showing you right here. Here is your object. Now let's increase the refraction, and you can see more and more of the object in your line of sight because of the higher refraction coefficient. This is
okay. Put a mountain in front of you, an actual physical curvature. See, this is what would happen on a flat Earth. That's exactly what would happen on a flat Earth. If you had something physical in front of you already blocking the object, and then you invoke refraction, it's not going to lift that distant thing above the thing in between you. It's a great example of how vision works on a flat Earth.
I don't think that it is, because literally the value, like the formulas used in this simulation, in the actual formulas, is the radius of the Earth. Inherent in the formulas used to make the simulation.
You know they're back engineered off the fact of our optics in the first place, right? That's exactly how it was engineered in the first place. Everything was engineered off flat Earth physics and then back engineered into globe things, and obviously it doesn't work because it doesn't work most of the time. But
you can say that, but I think that's just a claim. I mean, like, literally,
well,
how is
I can say that.
If it's in the formulas, the radius.
Well, because okay, so if you look back to the origins of it, you know, the ancient Greeks looking at ships disappearing over the horizon. That all started as an optical thing. Okay. And so, of course, that's where the ancient Greeks are the ones who gave us the circumference of the Earth in the first place, because they believed in it being spherical based on those three basic principles: ships disappearing over the curvature, stars will appear differently when you travel to different places, like all the rest of your scenery, and that some apparent shadow eclipsing the moon looks spherical, and we assume it must be the Earth because it only happens during a full moon, which is a fair enough assumption to make. Then that has proved the Earth is round. They were the three basic principles that Aristotle used to come up with the idea that the Earth is spherical. And that was when then Eratosthenes, who was nothing more really than a head librarian of the library in Alexandria, came up with the concept.
Wait. You know that the head librarian, you know that the head librarian for the Library of Alexandria is a lot different than the head librarian of just a modern library, right? Like the Library of Alexandria was much more closer to a research university institution than a library.
Yeah. Look, I got no problem with that.
Don't dismiss him as just the head librarian then, because the job description included a lot more than just what you would expect from a head librarian.
Well, he was
continue.
known as a jack of all trades and a master of none as well.
Okay, fine. If you want to keep taking pot shots at
he had a good
Aristotle,
general knowledge about a lot of things. But,
okay.
But yeah, continue. The point is that then all the assumptions were based on the fact that the Earth could be spherical based on the physical observation of the ships disappearing over the horizon was the first thing. So that's just a perspective thing. And so that's where it got back engineered from in the first place. If they had the Nikon P900 back in their day and see that the ship was visible much, much further, then they would have calculated the Earth to be much, much bigger and the sun much, much further. And everything would change, everything about it. But because it's all back engineered on the fact of normal human vision is at 6 feet high, we can see 3 miles to the horizon. That's where it all began. So that's where it all got back engineered from. And we've known for thousands of years. This is the typical thing you will hear from modern day astrophysicists. It's not okay to argue the Earth is flat. We've known for thousands of years. And it all goes back to that basic philosophy based on our vision of things appearing to disappear in the distance.
So what is your explanation for why things disappear over the horizon bottom up? And because if I'm just thinking about the law of perspective, right? And how perspective works. Typically, things are just going to get smaller and smaller and smaller until I can no longer resolve them. They don't disappear bottom up in perspective. So what causes, like with the sunset, to get back to that, what causes the bottom half of the sun to disappear first?
Well, as you actually showed, the way you shrunk your fingers, they go away from the eye. So when you got perspective, you got a perspective, it's a triangle. And it's a difficult thing to sort of explain because you can only see perspective through your own eyes. It's the only way it works. So visually, you're looking at a rectangle. Prospectively, it shrinks down to a singular point. So what's happening is everything beneath you is ramping up towards eye level. Everything above you is ramping down or sloping down towards eye level. And so assuming then an equal distant height, so you're 6 feet above the water, if the boat was 6 foot high, then it should technically meet at about 3 miles is the angular resolution limit where it will start to disappear. But what happens because things are above the line of sight, so that the line ramping in front of you always ramps up to eye level. That's just perspective. It's not actually physically ramping up, but to our eyes, that's what it's doing. And it will always be that way. No matter how high you go, it's always going to meet at eye level. So because things do get smaller and smaller in the distance, the things which are higher above that perspective convergence point where they sort of compress more and more into it, the things higher than it will still be seen. Whereas meanwhile, the things beneath you, especially on the water, you get waves and chop and everything, they're not shrinking at the same rate in the distance. So it will hide the bottom first.
So how do you explain
that's for a boat on water?
How do you explain images like this, which right here, right here, these green crosshairs, this is eye level. And so right here, you have the horizon below eye level. So things are not ramping up to eye level in this picture.
Yeah, well, but you look in the middle of the picture to see where the horizon is, and it's in the middle of the picture.
But right here,
eye level of that green cross is your height, that's your altitude.
This right here is eye level. This horizontal.
That's altitude. Yeah. So
that's eye level. That's a horizontal line from your eyes. That's the definition of eye level, and the horizon.
Yeah. But you're still missing the point, aren't you? Like the ground beneath you is ramping up to the center of the frame. See where those two little red lines are, either end of the frame? That's pretty much at your horizon. If anything, I think it's pretty well spot on. The horizon might be slightly higher. But this is definitively
showing that the horizon, that things do not go up to eye level.
No, you're using two incorrect terms, because eye level is the horizon, eye height is the green cross. So there's two different things. Your eye height is a different thing from eye level in perspective. So that's what the theodolite is for. It's a useful tool to overcome perspective, so to show your actual altitude, as opposed to what perspective does is makes everything draw to eye level. It has to.
So tell me what the difference is between eye level and eye height.
Altitude Like, obviously, the horizon is, how high are we here? 11,074 meters. So that green cross is showing what something in the distance, if it was 11,074 meters high, that's how high it would look. But eye level is the convergence factor of how we see. It's perspective. It's just the limitation. So because the sky is sloping down, the ground is ramping up, that's called eye level. But eye height is altitude, which is 11,000.
It really sounds like eye level and eye height are the same thing, honestly.
No, I know. But that's why you have to discern. There's eye height is altitude, eye level is perspective. Two different things. So again, that's why the horizon.
I'm not understanding the difference, because
the horizon is still in the center of the frame, right?
When I think of what eye level means, it's a horizontal plane at the same level as my eyes. So no matter how high I go up, that changes what eye level is. So in this, we're very high up, and the horizon does not, like you said, perspective means that the horizon will always go up to eye level. But here, it's not.
Yeah, well, that's a matter of semantics, isn't it? Like, if we interchange the words too easily, because generally speaking, eye level is, on ground level. But when we talk about height with altitude, it takes on a different meaning. But, in perspective, eye level will always be the center of the frame, exactly as shown in that picture where those two red lines either side of the frame are. That is eye level. That's why it's center of the frame. But eye height is the altitude, and that's what that other device, some sort of theodolite, is going to be showing for you. It's an assistance, but it's honestly, in the middle of the picture. Like that's eye level.
Changing the definition for eye level.
No, I'm just helping to define it more accurately.
But okay, so where are you getting your definition? Because it sounds like you're saying eye level just means wherever the horizon is, that is definitionally eye level. But like, where are you getting that definition from?
Well, somebody has to do it, and so I've done it.
So you're just redefining it.
I am describing it as it is. Whereas most people are using two different words to mean the same thing. Whereas altitude, when obviously that ground is well beneath your feet level, it's 11,000 and change meters beneath your feet level, but in perspective, your eye level is the horizon.
I don't know if I can get behind. I mean, I'm just using the standard definitions, the accepted definitions for what eye level means.
Yeah, science is always changing and upgrading. So, you might be helping in pioneering how we can reconsider the way we describe these things. It's a different thing from eye height to eye level. Your eye level obviously is where your eyes are, but your eye height is going to be different at different levels. So, it is just a matter of semantics. That's all it is. It's the way we describe things with words. Like previously throughout history, flight is only a relatively new thing. And even these instruments and, theodolites and stuff, and these, what do they call them? The eye heads up, whatever. But these are all relatively modern inventions. And so it often takes our language time to catch up with new advancements in technology. And this is where we're at. So the eye level is that where those red lines are, that's level, that's the 0 point. Eye height is where the green cross meets. Altitude.
Okay, so I guess I'm still not understanding how you get from there to how the sun sets. I'm not understanding how perspective explains that.
Well, okay, so generally speaking, we're on the ground. We're not up in the plane now, so we're on the ground. And that horizon is still going to rise to eye level. Doesn't matter how high you are up on a mountain, wherever. If you took a panorama picture with your camera held at eye level and flattened level, the horizon is always going to be in the middle of the frame. Now, in the distance, there might be mountains and trees and all sorts of different things getting in the way. And it's those obscurities that get in the way of the sun, because it is also on its perspective ramp. And the higher something is, the steeper that ramp appears. But it doesn't necessarily mean it hasn't also gone a great distance across, like it might be thousands of miles away, by the time it appears to go straight down, and it is still hidden by our ramp coming up, getting in our way and obscuring it, which would make it look as though the sun is going down. To me, it's a really simple understanding of perspective, that if you're in a room, especially, this one's not much good, but where my last place was with a flat roof, a flat ceiling, you look into the corner. If you sat on the floor and you look into the corner sinking down seems to be quite steep. The floor sort of ramps up a little bit, and you can eventually understand those lines will meet. Then if you stand up, that sort of changes a bit. The ceiling level looks a bit flatter and flatter. But if you then had a really massive ceiling, then the angle of perspective that line would follow, even though it's still a parallel line, is going to look steeper and steeper. And that's all the sun is doing. It gets further and further away because it's already so high. It's going parallel to the ground, but it appears to be going down into the distance. And then you've got a nearby point obscuring it. The sun's so far away, disappears, it starts to hide the light. So it goes dark.
But with perspective, what would really happen is that the bottom half of the sun would never be obscured. The sun would just get smaller and smaller and smaller as it got more distant. I agree that it would look like it's getting closer and closer to the horizon, but in perspective, the bottom half would never be obscured. You would still see the whole thing. It would just get smaller and smaller and closer, but the bottom would never be obscured.
Only if you got higher and higher and higher to the point of at least half the height of the sun. Then it would do that. But you are so low. That's the thing. You are so low to the ground, and the earth is so massive, it's so huge, that your perspective convergence point is only a few miles away. We tend to think that, we can see so far because we see the sun for half the day, but the sun is so high in comparison to us that the distance that it's already gone before it's converged is nothing. If you got higher and higher and higher and higher, you will see it disappear into a tiny convergence point, but we can't do that, generally speaking.
So what is blocking the bottom half of the sun during a sunset? What is blocking the light from reaching our eyes?
The land, the convergence point of what's beneath you converging up to eye level, which it does in 3 miles and 6 feet high. I'm thinking about
this in like, if the sun is small and local and it's noon somewhere else on Earth, right? That sun is directly overhead someplace else on Earth when I am seeing a sunset. So how could land possibly be blocking the bottom half of that sunlight from reaching my eyes if it's above the land?
Okay, so there's small and local, and then there's small and local. Like when we say the sun is small and local, we're saying it's not 93 million miles away and a million times bigger than the Earth. We're saying that it's an orb of light that we see, and I say through our firmament, which is only about 70 miles high above us, okay? So that's where it's making its apparition of light to us in our line of sight. So if say we had a glass ceiling in our house and we're looking up through to the sun, we see the apparition in the glass itself. And so if then it's a massive glass ceiling over a huge, huge area, then a person, 500 miles away looking up through that glass ceiling, he's going to see the apparition of the sun through a completely different part of the glass ceiling, which will create a different angle of light towards him than what you're seeing towards you.
Is this the firmament that you're talking about, this glass ceiling?
Yeah. So if I say that firmament is more like a flat sheet of ice about 70 miles above the entire Earth. And so if the sun itself is 3,000 miles high, then where we're seeing it from here up through this firmament down here, and somebody over here is seeing it through the firmament here, they're seeing their sun there, I'm seeing my sun here, but the sun is actually up here. So we're seeing the same thing through completely different places. And it's, for all intents and purposes,
it's something to do with optics, you think? That is like as it refracts or as it goes through this lens, that it's somehow
absolutely. Everything is optics. Everything is perspective.
Okay, so my question. Okay, I have several questions because one, I want to know: can you bounce radio waves off of the firmament? Can you bounce waves and get a measurement there?
It wouldn't surprise me if you could, but See, the thing is, we've got the atmosphere, and the atmosphere is a different gradient of things. I've done a long video on this, so I don't really want to bore you with how long it took me to work this sort of thing out. But basically, we've got different levels of the atmosphere. Our main one is about 12 to 14 miles high, and that's the breathable atmospheric gases that we live in. So if a pilot manages to take a plane up about that high, which I think off the top of my head is about 70,000 feet, that's when they say they've reached the edge of space where the sky stops fluorescing blue and goes black. And that's then a density gradient as well. So it's almost like a gaseous layer. And once you're above that, planes can't actually get lift from that because the air itself is too thin. So my thinking is that it's the same thing when you stick your head underwater and you hear sounds much louder. The more dense the medium is, the better waves propagate. So once you go up into such a thin medium, even radio waves won't propagate at the same speed and frequency as what they do down here in the dense atmosphere, what we live in. So if we send it up all the way to 70 miles high, which is, another 50, 60 miles, whatever, above that, then the radio waves are going to be so weakened, they're going to give the illusion of being, say, if we shot them at the moon, of being 240,000 miles away, when really it might only be actually 70 miles high. But it's the density of the medium creating that false sense of greater distance than it really is.
Can we not easily debunk this by just showing that light can travel through a vacuum, which has the absolute minimum medium density that you can get?
Yeah, but
light travels through it, no problem.
Again, is light traveling, or is the vacuum just nothing it? You know what I mean? It's like
I don't know what you mean.
Well, nothing exists, so there's.
I don't think it does, but okay.
In the vacuum,
I don't think a vacuum is not the same.
The definition of a vacuum is nothing. Okay.
It's not, but okay.
Well, it is, because
there's lots of stuff in a vacuum. It's just the minimal amount of stuff you can have.
Well, then it's not a vacuum.
well, it's again, it's a vacuum because there's a very small amount of stuff in it. There's still going to be.
So therefore, then light can pass through it. That's right.
Yes, vacuum can still a light can still pass through a vacuum, no problem. But if you're saying that the speed of light varies based on the density, but we can test that and we can observe.
I didn't say speed of light though, did I? I was talking about radio waves.
Radio waves are light.
No,
radio waves are light.
Well, why can't I see by my radio picking up a signal at night?
Because you only see in the visible spectrum of light, but there's radio spectrum, there's microwave spectrum.
Okay, well, my definition of light is being able to see in the dark.
Okay, well, that's
darkness, you got light, and so if it's not visible, then to me it's not light. But you call it by.
But we know that
light,
it's
and I'm
made
just going to say, well, you're full of shit. It's a form of radiation, but it's not light.
But we know it's made of the same stuff, photons. The only difference
it's a different vibrational frequency.
Yes, it's a different frequency.
You've got
it's the same stuff, just a different frequency.
Plethora of vibrational frequencies from the base up to the lightest, and different ones. Some are visible, some are audible, some are only audible through radios, and so on and so forth. That's why it's called radiation, even because
I get all that.
Just different frequencies. Yeah. So
here's the question:
but if you're going to call it light, then it has to be in the visible range for me to accept you as the definition of light.
Again, that's your definition. You keep redefining words, but fine for this
conversation. No. I'm just common sense stuff, mate. Common sense.
I know, but I'm just saying, light definitionally is photons. That includes radio waves. That's just definitionally in physics.
It's a photon.
Okay, fine. We'll move past that. I just want to ask.
What's a photon?
A photon is an excitation of the electromagnetic field. So it's
an ionized gas fluorescing.
No. It's not an ionized gas.
But it could be described as a photon, or
no. So when an ionized gas fluoresces, what's going on is what's going on is like electrons are going from high energy to low energy. And when they go from high to low energy, they need to emit a photon because energy needs to be conserved. So if they're going from a high energy to a low energy, the difference in those energy levels is emitted as a photon of light. And that's what you're seeing. So that's how that happens on a physical level. But
So
where I was going with
that's sort
that,
of pretty well said. Okay,
where I was going with that was what's very common in physics programs around the world is they'll do a moon bounce. Well, they'll take like a high frequency radio or microwave signal, which I would say is light. Okay, whatever you want to call it, it's made of photons. So, and they'll send that to the moon and bounce it off the moon and then detect it back. And it takes like 2 seconds or something like that. It takes a certain amount of time. So if there's a firmament overhead, then that would mess with like how is it that you can bounce something off the moon and then it comes right back to where you sent it out and you can detect it about 2 seconds later? So we could, how is that possible? And physics students all around the world do this very regularly.
Well, to me, I'm convinced that the moon is this side of the firmament.
Oh, so the moon is in the firmament. Okay, so then
we've got different layers of gases, right? And as they get lighter and lighter, helium and hydrogen are the lightest of them all. And I'm quite convinced that at the top of the underneath of the firmament would be a huge amount of helium, which would possibly become what they call a superfluid of helium. And that is what itself is what stops the moon from getting any higher. And because of that density of gas is actually so less dense, so light, again, we're going back to the word light. We're using it in different ways again, but light as a weight is less dense. Then that is what is going to affect the radio waves, the frequency of how they propagate backwards and forwards. So within 2 seconds, it still might only have gone 70 miles up and back and give you a reading of 240,000 miles away.
Well, again, we can test whether or not the density of medium affects the speed of light.
But we don't really have the scale of spectrum to be able to do it, apart from what we do actually have in our atmosphere all the way up to the firmament in the different layers. That's why I say, this 12 to 14 mile layer is quite near to us in comparison to way up to where the firmament is, to where the moon is, and where the sun itself propagates as a ball of plasma and light, which is why I think we generally consider the sun and moon to be about the same height, because they're virtually in the same layer.
Well, we can't
an apparition of light.
Yeah, I would just very much disagree with that. You can measure, like if you assume a flat Earth model, you would be able to measure like the angle to the sun, and where on Earth it's noon when you make that measurement. So you'd be able to have the distance between you and the location where the sun is at noon. So if you have the angle and you have the length, you can use trigonometry to calculate the height of the sun when you made that measurement. Right?
Yeah.
That's basic trig.
Well, okay, but you missed the fault in that problem. When I've described the firmament as 70 miles high from each position, but the sun is 3,000 miles high, and each person is seeing the sun at the 70-mile height, they're both assuming they're seeing the same sun in the same spot, but they're not. They're seeing it in a completely different spot. And that's not a triangle. That's a huge rhomboid or trapezoid or whatever you call it. That they're not even looking at the sun, because you can't see the sun through the firmament. You can only see it in the firmament, which is much, much closer than what it actually is. So you're always looking at an apparition of light, which isn't really actually there, giving you a false indication of where you think it might be, which will falsely give a reading of it being millions of miles high when opposed to being only 70 miles.
Okay, so then do you propose any kind of test or measurement that could be done to detect the firmament? Can we bounce radar off of it? How can we detect if the firmament is there or not?
It's a difficult one. The best evidence I've seen so far is that Go Fast rocket that went up in 2016, and it gave a reading of 73 miles high, and it hit a sudden clunk and stopped, and then slowly tumbled back down again. That's the best